Okay, I left this slide in. We're not going to do any homework on this, but I just want to make you aware that we deal with these trusses, and we're going to deal with them as two-dimensional objects. Well, they do have what are called space trusses, and they're three-dimensional objects, so you can start putting forces in off-axis. It no longer has to be in the two dimensions. Be aware that it's there, but we're not going to deal with it much in this class. Okay, so now we've done trusses. Let's talk about frames and possibly machines. Okay, frames and machines are structures with at least one multi-force member. Okay, so again, what's a multi-force member? It's a member that contains at more than two forces. Frames, the difference is frames are designed to support loads and are usually stationary. Machines contain moving parts and are usually designed to transmit and modify forces. The analysis you can find is the same between the two. So this is a frame. Why is this a frame? Let's look at this. Okay, is this a multi-force member, a three-force member? Nope, it is not, right? There's just a force here and here. What about this one right here? Well, you got a force here, here, and here. One here, 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 and here. So you got a bunch of forces. So this is clearly a multi-force member. What about this one? This is just a two-force member. Again, very helpful, so you know the forces align in this direction. And what about this one? 1, 2, 3 forces on there. So this is definitely a frame. Okay, internal forces are going to be considered here. This is going to be the first time, throughout this this course we've been ignoring the internal forces, but for these frames and machines, we're going to start considering the internal forces, and we're going to figure them out by dismembering the frame and creating free body diagrams for each component. Okay, so here we have this portion right here. We're going to take just right here, right? It has a tension going off this direction, it has AX and AY. You'll notice this is on a pin, so there's no moment there. Here at this point we have CX and CY, and here we have force at BE. Now we're going to take this portion. Now this is where it's very, very important, right? Equal and opposite. So CY is up, CX is down, is to the right. So therefore the C that this is feeling is in down in CY and to the left of CX. And so that's very, very important, is that you have equal and opposite forces going on. And they're the same values. CY is CY, CX is CX, but the directions are in the opposite direction. And then same here, you have this member, they drew it in compression, right? The member's getting squished. And so that's going to cause a force here off in that direction. It's going to cause a force off here in this direction. But as far as this member is concerned, it's getting squished in this direction. So forces on two force members have known lines of action, but unknown magnitude and sense. So what we have one two force member, right? It's this one right here. So it's nice. You'll notice we have CX and CY here. Here we just did force and BE because it's a two force member, but you know the direction. It's going to be in that direction. Okay. But forces on multi-force members, again here this one is a multi-force member, right? So they have unknown magnitude and line of action. So you have to give it a two unknowns, CX and CY. And forces between connected components are equal and have the same line of action but opposite sense. Exactly what we just talked about. Here, this CY, you have the opposite, equal and opposite. This CX, you have equal and opposite. So sometimes we're going to use this to do work on these frames which cease to be rigid when detached from their supports. Okay, so look at this. This is actually a really cool example. You have is this a truss? Well, it is not a truss. Why is it not a truss? They're both two force members, right? Well, they're not two force members. They're both straight members with pins at the end, but the problem is you have force in the middle. So this all of a sudden becomes a three force member, and so this cannot be a truss. So what happens with this thing? You push on this, nothing's going to happen, right? But you start getting rid of either one of these things, and it's going to move. The free body diagram, and so when you do a free body diagram of all this thing, you end up with that you have four unknowns, right? You have AX and AY, you have BX and BY, and so we have four unknowns. Well, this is a problem because we've made a big deal about how you can only do three equations and three unknowns. So what do? Well, if you break this up into two distinct but related rigid bodies, what does that mean? You have your AX and AY, right? This is it. Here, you'll notice we broke up the C, so you have a CX and CY. But now how are these related? Well, here you have the same magnitude, equal and opposite. You have negative CX and minus CY. So these are the same magnitudes of both, but in the opposite direction. And then you have BX and BY. So what does that give you? Well, over here we have 3 equations and 1, 2, 3, 4 unknowns. Okay. Over here we have 3 equations and 1, 2, 3, 4 unknowns. But if you actually look at it, you have 1, 2, 3, 4. These are the same as there, so 5, 6. So you end up with 2 sets of 3 equations, and so you can solve for a total of 6 unknowns, and that's what we have. We have 6 unknowns and 6 equations, and so you can actually solve for it. The equilibrium requirements for the 2 rigid bodies will give us the 6 independent equations. So we can actually solve for this as we just said. So let's look at an example of this. Example 6.4, we have this frame.